How many of you have ever pushed the wooden benches in the gym, the ones that have a little bit of carpet underneath them, that are at the back of the gym often, sliding them around? Okay, so those of you that have, let's use our imaginations. Consider, let's pretend this bench below is one of those wooden benches. And you know what? Let's pretend Jackson's the one pushing them. So student number 1, Jackson, is pushing it across the gym. It's a rough surface, it's smooth, but there is friction. You can feel it resisting you. So rough is me just saying, assume we're not on ice at a constant speed. You know what? We should probably underline the phrase constant speed. That's important. Suddenly, student number 2, Kenley, comes along and he pushes down on the bench. Better yet, Kenley comes along and sits on the bench, because that's another way to apply a constant force. If Jackson maintains the same original constant force as before, what's going to happen to the weight, the normal force, the force of friction, and the motion of the bench? That's our question. Let's do these systematically one at a time. Let's put a little letter A right here. You know what? I think this is a job for a Freebody diagram. Now, originally, before Kenley comes and sits on it, we have gravity down, we have normal force up, we have Jackson pushing with an applied force, and we have friction going this way. What could you tell me, if I was really good with graphics, about the length of these two arrows? The length of Jackson's applied force forwards and the length of friction pointing backwards. They would be the... Antonio, why? What 2 words? I have no idea what you said. Why? What 2 words? What 2 words? Okay, constant speed. Okay. Now, along comes Kenley. And let's pretend this is like 1/100th of a second after Kenley is sat down. So a split second after. What are the forces acting on this bench? Get the obvious one. Okay. What else? Bigger, small, normal force, you said? Bigger, smaller, or the same size as mg? Well, are we sinking into the ground like quicksand? Are we flying into like Superman? So vertically, the forces have to be balanced. But do you notice now there's 2 downwards forces? Can you see it? Can you see it? There's mg, and then there's Kenley. So I'm going to argue the normal force is going to be bigger. If I was going to be really fussy, Jackson, I would try and make it the same length as those 2 combined, but I just tend to make sure I want to know that it's bigger. What would happen to the force of friction? Bigger, smaller, or the same as this one? Why bigger? Friction is what times what? Mu times the normal force. Did the normal force just get bigger? Okay, so I'm going to go like this and exaggerate it. You okay with that, Jackson? Okay. Kenley, I'm coming to you because you're the meathead who's sitting on the bench. You ready? A, what happened to the weight? Now, when I say weight, when I use this word, what's this a synonym for? Which force exactly? It's on your green sheet if you forget, but it's worth committing to memory. Yeah. So Jackson, Kenley. I'm going to Kenley now. When I say weight, I mean mg. Did the mass of the bench change when you sat on it? Did the mass of the bench change? So did the weight of the bench change? Say, did the mass of the bench change? So did the weight of the bench change? Let's say no change. Kenley, look at the normal force before and after. Did that change, or did that stay the same? Bigger or smaller? Normal force, my abbreviation for got bigger is an arrow pointing up, increased. Why did it increase? Because the bench didn't sink into the ground like quicksand, and it didn't fly into the like Superman, and so the forces did have to be balanced, but since you were applying an extra downwards force, the ground had to apply an extra upwards force, just the same as when before I started teaching, when I tried to pull on this table and they pushed down on it. Kenley, what's going to happen to the force of friction? Friction is what times what? Okay, you got your formula sheet out? So can you find the force of friction in the forces little line there, kiddo? Someone should have been watching some video lessons this weekend. Someone has a long weekend sort of coming up on Parent-Teacher Day. You can be watching some of those on Thursday. So on the front page, so you'll see F equals MA. And then right next to it, it's about halfway down, I think, yes? You'll see F net equals MA. And then right next to it, I think you see weight equals F force of gravity equals mg, yes? And right next to that is friction. Friction equals what times what? Mu times the normal force. Friction equals what times what? Say it out loud. Mu times the normal force. You're going to say it one more time because you've been away and it's not to make fun of you, but to help it stick. Friction is what times what? So mu, this strange thing here, times the normal force. Now, what did you tell me happened to the normal force in part B? It got, so what's going to happen to the force of friction? Why? Because it's mu times the, okay. Good. You see how we put all that together? Some thinking there. Oh, you know what? I don't need to write friction. FR increases. Okay. By the way, I know a number of you have course planning appointments and things. Just sneak out. Let me know ahead of time, but sneak out if you can. So now, all of us, we're going to decide the last part here. What's going to happen in this free body diagram? Which way must this bench accelerate? Be obvious. This is going to accelerate forwards? I'm saying to you right now, all of your answers are impossible. Look at this free body diagram. Don't overcomplicate it. Which way must it accelerate? To the, I'm looking for it starts with the letter L. Okay, it's going to accelerate to the left. Now, which way was it traveling? Forwards. If it's accelerating to the left, what's going to happen? It's going to, okay, it's going to slow down, and then very rapidly, it'll come to a stop. Okay, but when someone says it's not going to go anywhere, not yet, we're like 1/100th after Kenley has jumped on it, it's going to slow down and stop. And there's the, now that's kind of a Captain Obvious. Kenley, you could have made that prediction without even doing the experiment. Yeah, if I sit on the bench, it's going to stop and Jackson's going to punch me. Or whatever. But there's the physics of why that occurs. Okay? What you did was not increase the mass of the bench. You increased the normal force, which then increased friction, because that's mu times the normal force, which gave us Newton's first, an unbalanced force to the left. We have to slow down and then come to a stop. It says explain your answer using principles of physics. I think we just have in our discussion. Is that okay, Courtney? I'm going to be a little bit technical here. We've been saying that mu, the coefficient of friction, is what talks about how sticky one object is in relation to another. There's actually two types of mu, of coefficients of friction. There's friction on an object that's sliding, and there's friction on an object that's at rest. Let me pause the video for a second. Question in just a second, so get your physics brains working. Here's what it says. There can be friction on an object even when it's at rest, because those hills and valleys will lock up when we apply even a small force to an object. The force of friction on an object at rest is called static friction, because the word static means not moving, not changing. So let's suppose, I'm going to do this experiment with their table in just a second. Suppose I pull on that table with 2 newtons and the desk does not move. Which of the following is true? Let's pause the video again. Which of the following is true? A, static friction is bigger than 2 newtons. B, static friction is exactly 2 newtons. C, static friction is less than 2 newtons. Or D, there's no static friction at all. Once again, we're going to vote. Once again, how high holding the hand up is how sure you are of the answer. So when I pulled on that table with 2 newtons and it didn't move, is friction bigger than 2 newtons? Is friction equal to 2 newtons? Is friction less than 2 newtons? Or is there no friction? And I didn't say the word static so I wouldn't confuse you. It's just a type of friction, but it's friction. Got the argument, Courtney? Who says A, Mr. Dueck? Static friction is clearly bigger than 2 newtons because it didn't move. A, 1, 2, 3, 4, 5, 6, 7. Ooh, this will be a little controversy here. Who says, no, Mr. Dueck, static friction is exactly 2 newtons? 1, 2, 3, 4, 5, 6. Ooh. Who says it's got to be less than 2 newtons? Who says There's no friction at all. You know what? Let's use a process of elimination. Why must D be wrong? First of all, if there's no friction, what surface am I imagining that we're on usually? Ice. It's not on ice. If it was on ice, I could give a little tug and it would just keep sliding. So I agree with those of you who did not pick D. I agree with that. Why must C be wrong? If static friction was less than 2 newtons, which way would that table accelerate? Forwards. A or B? Convince me. Yeah.
B, because you don't need a lot of force to move an object with like the friction.
I agree with your answer. I don't know if I agree with your explanation. What if A... Oh, Antonio, yeah, go ahead. I think we can go to newtons first. Let me pause the video again. What was the correct answer? A, B, or C, or D? What did we say? Why? So, no acceleration means forces are balanced. By the way, I've just paraphrased or described one of Newton's laws. Which one of Newton's laws is that one right there? Yeah, so if you said Newton's first and you drop the mic and walk it off, I'd give you full credit for that. But what does Newton's first say? Hey, if you're not accelerating, the forces are balanced. If you are accelerating, you have an unbalanced force. Static friction acts when you have 2 objects at rest to one another. So static friction, for example, that's what holds a car with its parking brakes and keeps it from sliding down the hill. If the hill was icy, it would slide down the hill. We saw a video to that effect a couple of days ago, right? A block of wood will remain stationary on a sloped table until you increase the angle so much that friction can no longer cancel out gravity. This force to overcome static friction is always greater than the force needed to balance sliding friction. Sliding friction is called kinetic friction. And we think this is because to overcome static friction, you have to break the welds that are kind of holding the object, the 2 surfaces together. So, mu s equals static friction at rest, mu k equals kinetic friction, and this is when we are moving. I'm being, Courtney, pretty technical here now, but I'm trying to help to explain why it is that once you start something sliding, it's easier to keep it sliding. So here I said this, a 5 kilogram object sits on a surface with mu static 0.3 and mu kinetic 0.25. Courtney, which one is bigger? Don't overcomplicate it. So the second one, once you get it moving, you'll find the force of friction is a bit less. You don't need to push as hard. Okay? A says, determine the force required to move the object. So right now it's at rest. This is a job for a free body diagram. What are the forces acting on this object, Courtney? Get the obvious one. What else? Normal force? Are we sinking in the ground like quicksand? Are we flying in the air like Superman? Right? And here I think they're the same. I don't see Jackson or Kenley sitting on the bench or anything like that. We're pulling on it, and this is what they want us to find. It says determine the force required to move such an object. I'll call that the applied force. How big a force do we need to apply? Is there friction? Well, they've given me 2 coefficients of friction. That's their way of saying make sure you include the force of friction. Which way should I have friction pointing, Courtney? Which way are we trying to pull it? To the So which way would friction be acting if it's resisting us to that? Yes. Okay. And I think initially friction will be the same size because part A, let's pretend it's just about to start to move. It's the split second before it starts to move. Determine the force required to move an object. Okay? So for part A, don't write this next bit down, just look up. We would normally say, who's winning? Well, maybe the applied force, don't write this down. And then we would say, who's losing? Friction. And then we would say, don't write this down. What does winner minus loser always equal? Except if I just haven't quite started moving yet, I'm just about to, what's my acceleration as a number exactly? And so what's m times 0? And so you would have that, and then you could just plus this over to that side, pick your pencils up, or you could have just said, you know what, at the beginning it's a tie. And that's really where that equation comes from. It's saying, look, right now we haven't started accelerating, it's a tie. Kenley, friction is what times what? So, mu times the normal force. Which of these two mu's am I going to use? Have I started moving yet, Courtney? So which one of these do I use when we're at rest, when I haven't started moving? The mu static. So I'm going to get this mu static. Oh, wait a minute. I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. Which one? Okay. What's mu? I don't know. What's mu with you? What's mu? 0.3 or 0.25? Which one am I going to use? Yep. And m was 5 kilograms, and g is 9.8. How hard do I have to pull to get this thing moving? Someone has said 14.7. Someone else want to double check? Sorry? 14.7 even? What if you only pull with 5 newtons? Will this move? No. How big will friction be? Will it be 14.7? No. If I pull with 5 newtons and it doesn't move, how big must friction be exactly? 5. Then I pull with 8 newtons. How big will friction be? 8. Friction is only as big as it needs to be to try and cancel out whatever we're doing. So B. Suppose I pull with 10 newtons. Find the acceleration. Jabber. No calculator required. In your head, if I pull with 10 newtons, what will the acceleration be? How big is the force of friction? So if I pull with 10, what will my acceleration be? You had it 30 seconds ago. You were in this. Adam, why 0? I haven't overcome friction yet. And how big will the force of friction be, Jabber? Don't say 14.7. How big? Huh? No, it can't be 0. How big must the force of friction? Has to be the 10 to cancel out the 10 that I'm pulling with. What if I pull with 11 newtons? You know how big friction will be? 11, what will my acceleration be?
0.
In fact, when will this start to move? Courtney, if I pull harder than what? So if I pull with 14.71, it's going to start to slide. As soon as it starts to slide, now friction gets smaller because instead of using the 0.3 to figure out friction, I'm going to use... Okay, so in C, in part C, Carlos, how hard are we pulling with?
20 newtons.
Are we going to be accelerating and sliding or not? Okay, so now, since we're sliding, we're not going to use the static coefficient of friction. We're going to use the kinetic coefficient of friction. Who's winning? Who's losing?
Friction.
And in this case, technically, this arrow would be shorter. I didn't redo the diagram. I think I can just imagine my way there. What does winner minus loser always equal?
MA.
What is what does C want me to find?
The force of friction.
And the?
Acceleration.
Okay, let's find the force of friction. Friction, Kenley, is what times what? I can't hear you. Mu? Mu times the normal force. Which mu am I going to use? Now that we're moving, I'm going to use the kinetic, the moving mu, which is 0.25. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which one?
Gravity.
We're running out of room, so let's go to numbers. Force of friction, once we get it moving, is going to be 0.25 times 5 times 9.8. When it was at rest, Courtney and I figured out that the force of friction, because it was canceling out the applied force, must be exactly 14.7 newtons. But once we get it moving, can you see it's gotten smaller? That's why things are easier to slide once you get them moving. Sorry, that's why things are easier to keep sliding once you get them sliding. Anybody else 12.25, or am I wrong? Someone else got that too? Yeah, I see a nod. Okay, so there's the first part. Find the force of friction. Gotcha. What's the second thing it wants me to find?
Acceleration.
How do I get the A by itself?
Divide the M.
And I'll get the acceleration is the applied force minus friction divided by the mass. In part C, what was the applied force, Carlos, my friend?
20.
Minus friction is 12.25 divided by the mass. Maybe I'll do that in my head. Let me see. It's going to be 20 take away 12 is 8 take away 7.75. Dividing by 5, that's the same as timesing by 10 dividing by 2. So it's going to be 77.5 divided by 2, 37.25? No, sorry, 3.725. I missed a zero there. I gotta do this one. I moved a decimal around, Mr. Dueck. Oh, I'm totally off. Wow, 1.55. It's completely off. Good stretch, Kenzie? Good. Yeah, I guess you can all turn the page, I guess. So that's my attempt to help you wrap your brain around, Antonio, why it's easier once you start something sliding to keep it sliding. Because friction technically is a tiny bit smaller. It's technically a different coefficient of friction once you're moving. Having said all that, to keep the math nice, I'm going to treat both types of friction as the same thing. I will not, on a test or a quiz, give you two different coefficients of frictions and say to you, figure out which one belongs with which. I might in the homework. So, friction, Kenley, equals what times what? Mu times the normal force. Where mu equals the coefficient of friction. I don't care whether it's already moving or it's at rest. I'm going to treat those as the same situation. And Fn equals, I don't have an equation for Fn. How have we figured out the normal force every time? I think I've said something like, I don't know the normal force. Oh, but look. Sorry, how do we figure out the normal force? No, it's not the normal force. I use something. 3 words. Middle word is body. I like example 4, I like example 4, I like example 4. Example 4 is a nice question. Sam, what's the difference between 4A and 4B? What?
Force?
Yeah, there's an extra vertical force. You know what? Normal force is not going to be mg. Do you know how I know? There's an extra vertical force. Normal force is not going to be mg. Okay. It says find the maximum force of friction between the mass and the ground for the following objects. And then I wrote here, technically this is static coefficient of friction, static friction, because we haven't started moving yet. Okay. You know what? Let's go like that. Riley, what does A want me to find? What does the whole question want me to find? You know what this is a good job for? What are the forces acting on this first diagram? Riley, my friend, get the obvious one. I agree. Are we sinking into the ground like quicksand? Are we flying like Superman? No, you say. So everything up has to equal everything. So I know there must be a force up the same size as gravity. What do we call that one, Riley? Yep. And there were no other vertical forces. I did a quick check. By the way, when I get to part B, that's a tougher question. What else? Well, it wants us to find the force of friction. So, okay. Kenley, friction is what times what? Riley, do I know mu, the coefficient of friction in this question? I don't know the normal force. Oh, but look. I know the force is the same size as the normal force. What force is the same size as the normal force? So here I can go mu mg. It's going to be 0.35 times 8 times 9.8. What's the maximum force of friction that we can have between the box and the floor? Savannah, what'd you get? Sorry, I missed that. 27.44. Anybody else? I'm going to carry some extra sig figs because I want to compare what's going on. So normally I'd call it like 27 or 27.4, but I'll carry 27.44 this time. Units, Riley, it's a force. Yep. Yeah. Antonio, you ready for the big leagues? Okay, let's do B together, my friend. What's it asking us to find? Force of friction. Friction is what times what? Mu times the normal force. You know what? This is a job for a free body diagram. What are the forces acting on this, Antonio, my friend? Get the obvious one. I totally agree. Is it sinking into the ground like quicksand? Is it flying like Superman? Then everything down has to equal everything. Okay. Normal force pointing up. Is there an extra vertical force, Antonio? Then all bets are off. Is the normal force going to be bigger, smaller, or the same size as mg? Convince me. How many forces do you have pointing down? So the normal force is going to have to not just cancel out gravity, it's also going to have to cancel out how big a force exactly in newtons. It's also going to have to cancel out how big a force exactly in... What? Okay. So I'm going to draw my normal force. Let's try that again. So it catches my eye. Antonio, are we sinking to the ground like quicksand? Are we flying here like Superman? Then everything down has to equal everything. So here's my equation. Everything up has to equal everything down. Is the normal force equal to mg this time? No! That's why you've never heard me say, friction is mu mg. It's not. It's mu times the normal force. And last day, the normal force is always equal to mg because those are boring questions. Let's crunch this, Antonio. It's going to be 8 times 9.8 plus 55. How big is the normal force here? What'd you get, Antonio? Or are you still writing? Sorry. Well, 8 times 9.8, that's going to be 80 times 10 minus 1.6. It's going to be 78.4. 78 plus 55, 128.4. 133.4? Yeah? How big is the normal force? Say it again. How big is Fn? So you do have an Fn clue? Cool. 133.4. You found Fn? That's not what they wanted us to find, though. What did they want me to find? The maximum force of friction is what times what? Kenley. Mu times the normal force? I don't know the... Wait! Yeah, I know the normal force. It's 133.4. Do you see how we went through that earlier? Okay, so now I can say friction equals mu times the normal force. What's mu? I don't know. What's mu with you? 0.35, and I can tell you exactly how big the normal force is. It must be 133.4 newtons. .35 times 133.4 newtons. And I get 46.69. I'll call it 46.7. What happens if I pull with 46.8 newtons? This will start to accelerate. In fact, if you were pulling with 46.7 exactly, you could feel through your hands, if you had a rope attached to this, you could feel, oh, it's just about ready to start to slide. You may have experienced that sometime if you've been pushing on or pulling on something and you're like, I can tell it's almost ready to go. Just need a little bit more. So I like B, I like B, I like B, I like C, I like C, I like C. Franz, what's C want me to find? Okay, friction is what times what? I don't know the normal force. This is a job for a free body diagram. What are the forces acting on this box, Fritz, my friend? Franz, my friend. Did it again. Get the obvious one. I did it twice, I think, too, didn't I? Wow, I caught myself after. Franz. Gravity, you say? What else? There is a normal force. Is it going to be bigger or smaller or the same size as mg? Why? Because 55 newtons is already being taken care of by somebody else from off the page. So the normal force is going to be smaller. Are we sinking into the ground like quicksand? Are we flying at you like Superman? No. So that means everything up has to equal everything. What is everything pointing up? There's two of them.
55.
So you're saying 55 plus normal force equals, what's everything pointing down? How would I get the normal force by itself? Did you hear him? What did he say? So you're telling me that the normal force is going to be mg minus 55? Cool. M was 8 times 9.8 minus 55. Here, the normal force is going to be 23.4 newtons. And I can plug that up into here. Hey, Franz, what's mu? I don't know. What's mu with you? What's mu?
0.5.
Yep. And then 23, was it 23.4 even? Yep, 23.4 even. When you lift up on an object, friction does get smaller. In this case, by how much? I got 8.19. Newtons. Way smaller. From 46.7 newtons to 8.19 newtons. So let's put this all together. To get object A accelerating to the right, I would need to pull harder than how much? So everybody look at diagram A. Courtney, how big was friction in diagram A exactly? So if I wanted to get it moving, I would need to pull with more than 7 point, yep. What if I wanted to get diagram B moving, Logan? By how much more would I need to pull? Or what would I need to pull harder than?
15.
Yep. I think you were back for that. I may be wrong, and if I'm wrong, I apologize. I was kind of trying to get you back and involved. Do you have the stuff written down for B or not? Okay, sorry about that. Adam, how hard would I have to pull to move object B? Stronger than what? Yep. And Antonio, how hard would I have to pull? Kevin's going to put a phone away, by the way. How hard would I have to pull to get part C moving? I thought you were looking at your phone. Am I wrong? Okay, I apologize. How hard would I have to pull to get part C moving? Harder than? Sorry? Yep. And each of those, if you wanted me to be fussy, Kenzie, each of these are an example of static friction because they're starting out at rest. And then once you got them moving, the coefficient of friction would technically change. But I'm not going to give you one on a test or a quiz where that happens, only in the homework. That's being physics correct, but fussy. Yeah. Quick, funny. Ooh, got lots to do still. I don't know if I'm going to get through it all. I got 17 minutes, roughly. A little longer. Okay. Put your pencils down, look up. I'm going to pause here. But if you want to get a head start, now many of you owe me many assignments. If you want to get a head start, I'm going to assign almost all of these homework questions. But for now, you can try number 1. You're capable of doing number 1. Your hint to find the normal force is it's a job for a free body diagram. You might reach the point where you can imagine the free body diagram in your head. I'll live with that in your homework, but I got to be honest, Jagger, on a test or a quiz, the 1 second it takes me to draw that free body diagram, it's so worth it. I always will. And yay, it's drawing. I mean, I still like to draw, right? 2 is okay. 3 is okay. 4 is okay. Yeah, we'll go there. And then I notice 6 and 7, we're mucking around with the normal force an awful lot because I see extra vertical forces. Same with 8, 9, 10. I'll assign some of those next class as well. Okay?